In physics, there is a prediction so strange that many scientists once hoped it was wrong. According to the fundamental laws of thermodynamics, a finite universe should eventually reach a point where nothing new can ever happen again. Not because it is destroyed, not because it collapses, but because every usable difference in energy slowly disappears. Stars stop forming, galaxies go dark, motion fades as temperatures equalize across space. The universe continues to exist, yet the processes that once created structure quietly shut down. This outcome is known as thermodynamic equilibrium, a state where matter and energy remain, but no physical process can produce anything new. The idea emerged in 1865 when German physicist Rudolf Clausius formalized the concept of entropy. While studying heat engines, Clausius discovered a pattern that appears everywhere in nature. Whenever energy flows, it gradually spreads out. Hot regions cool, pressurized systems relax, organized energy disperses into more uniform states. At first, this principle seemed limited to laboratories and machines, but Clausius realized something much larger. If thermodynamics governs all physical systems, then it must also govern the largest system of all, the universe itself. That realization carried a remarkable implication. If the universe is finite and follows the laws of thermodynamics, then over immense timescales energy differences everywhere should fade. The gradients that power stars, drive chemistry, and allow structures to form would slowly flatten. In everyday terms, complexity depends on imbalance. A star shines because its core is hotter than the space around it. A planet maintains weather because sunlight heats its surface unevenly. Life itself depends on delicate chemical differences that allow energy to flow through cells. Remove those differences and the processes stop. For decades, this prediction remained mostly theoretical. But during the 20th century, astronomers began measuring the universe with increasing precision, mapping galaxies, detecting ancient radiation, and observing the expansion of space itself. And gradually, those observations began pointing toward a startling possibility. The universe may not remain active forever. Instead, it may be slowly drifting toward a distant era where change itself becomes impossible. Yet this conclusion leads to a deeper mystery, because the same universe predicted to end in stillness has somehow produced galaxies, planets, life, and conscious observers capable of asking these questions. To understand how that contradiction emerges, we need to go back to the moment when scientists first realized that the cosmos itself is not static, but evolving. In 1877, Austrian physicist Ludwig Boltzmann wrote a single equation that quietly changed how scientists understood the fate of the universe. The equation connected entropy to probability. It showed that disorder is not just common in nature, it is overwhelmingly favored by the mathematics of reality. Boltzmann demonstrated that systems naturally evolve toward the state with the greatest number of possible arrangements. A highly ordered system can exist in only a few precise configurations, but a disordered system can exist in countless microscopic variations. Over time, probability pushes systems toward those vastly more numerous states. This idea transformed entropy from an abstract thermodynamic rule into something deeper, a statistical law of nature. To understand the implication, consider a library archive containing millions of documents. If a powerful storm scatters those pages across the floor, the pages will land in an enormous variety of random patterns, but the chances that they would accidentally reorganize themselves back into the original labeled folders are almost zero. Order requires specific arrangements. Disorder allows almost anything. Boltzmann realized the same logic applies to energy and matter everywhere in the universe. When energy spreads out, it gains access to far more possible configurations. A uniform state is simply more statistically likely than a structured one. This leads to a striking conclusion. Complex structures, stars, planets, and living systems, represent extremely rare arrangements of matter. They exist only while strong energy gradients keep pushing against the natural statistical drift toward equilibrium. In the late 19th century, this realization deeply unsettled physicists. If Boltzmann's reasoning applied universally, then the cosmos itself must be evolving toward maximum entropy. Eventually, the gradients that power stars and chemistry would disappear. At that time, however, scientists still believed the universe was static and eternal. The thermodynamic predictions seemed to describe a theoretical limit so distant that it felt almost philosophical. But during the 20th century, astronomy began revealing something far more dramatic. The universe was not static at all. It was changing, expanding, and evolving on enormous cosmic scales. And those discoveries would turn Boltzmann's statistical insight into one of the most profound questions in modern science. Because once the universe itself became part of the thermodynamic system, the implications became impossible to ignore. If entropy always increases, then the history of the cosmos must be moving in a specific direction. To see that direction clearly, scientists first needed to measure the universe itself, its motion, its structure, and its origin. That discovery would arrive in the early 20th century, when astronomers began observing something unexpected in the light of distant galaxies. In 1929, a quiet observation at Mount Wilson Observatory permanently changed humanity's understanding of the cosmos. Astronomer Edwin Hubble had been studying the light, coming from distant galaxies, using the 100-inch Hooker telescope, the most powerful telescope on Earth at the time. What he noticed was subtle, but the implication was enormous. The light from nearly every distant galaxy was shifted toward the red end of the spectrum. This phenomenon, known as redshift, occurs when light waves stretch as an object moves away from an observer. The same effect can be heard when a passing siren changes pitch as it drives past. Except in this case, the stretching happens in light rather than sound. Hubble carefully measured the distance to dozens of galaxies and compared them with their redshift. The pattern was unmistakable. The farther away a galaxy was, the faster it was moving away from us. The conclusion was unavoidable. The universe itself is expanding. Before this discovery, many scientists believed the cosmos was eternal and unchanging, a vast, stable backdrop where stars and galaxies simply existed. Hubble's measurements revealed something far more dynamic. Space itself was stretching, carrying galaxies apart like distant points on an ever-growing cosmic landscape. This observation immediately changed the thermodynamic story. If the universe was expanding, then the cosmos was not a static container slowly approaching equilibrium. It was a system evolving over time, forming galaxies, igniting stars, and continuously reshaping its structure. Suddenly, the universe had a history. And if it had a history, it might also have a beginning. Throughout the following decades, astronomers began searching for evidence of what that beginning might have looked like. Telescopes became more powerful. Radio detectors scanned the sky for faint signals from deep space. Then, in the mid-20th century, a discovery arrived that confirmed the universe had once been dramatically different from the cold cosmos we see today. It was not found in a distant galaxy. It was found in the faintest background glow of the universe itself, and that signal would reveal the earliest chapter of cosmic history. In 1965, two radio astronomers at Bell Telephone Laboratories encountered a signal they could not remove. Arno Penzias and Robert Wilson were testing a large horn-shaped antenna in Holmdel, New Jersey. The instrument had been designed to detect faint radio waves from space, but no matter where they pointed it, the antenna produced the same persistent background noise. They checked every possible source of interference: urban radio signals, atmospheric effects, instrument calibration errors. At one point, they even cleaned the antenna itself, removing debris left by nesting pigeons, convinced the disturbance might have a mundane cause, yet the signal remained. It was faint, uniform, and appeared to come from every direction in the sky. What Penzias and Wilson had unknowingly detected was the cosmic microwave background, the oldest light in the universe. At nearly the same time, physicists at Princeton University, led by Robert Dicke, had been predicting that such radiation should exist. Their calculations suggested that if the universe had once been extremely hot and dense, the early cosmos would have left behind a faint thermal glow as it expanded and cooled. When the two teams compared results, the conclusion became unavoidable. The universe had once been dramatically different from the cold, structured cosmos we observe today. Roughly 13.8 billion years ago, all matter and radiation were compressed into a much hotter and denser state. As the universe expanded, that radiation stretched and cooled, eventually becoming the microwave background, now detected by radio telescopes. Modern satellites such as COBE, WMAP and Planck later measured this ancient radiation with extraordinary precision. They found temperature variations of only 1 part in 100,000, tiny fluctuations that later grew into galaxies and clusters of galaxies. The statistical confidence of these measurements exceeds 10 sigma, making them among the most certain observations in modern science. But the microwave background revealed something even deeper. The early universe was not in equilibrium. It contained temperature differences, density variations, and strong energy gradients. Exactly the conditions required for structure to form. Stars, galaxies, and eventually life could only emerge because the cosmos began in this highly ordered state, and that realization sharpened the paradox. If the universe started with such delicate structure, and if thermodynamics drives everything toward uniform equilibrium, then the cosmos may be slowly drifting away from the conditions that made complexity possible in the first place. To understand how quickly that process might unfold, scientists needed to measure something even more surprising about the universe. They needed to determine whether cosmic expansion was slowing down or accelerating. In 1998, astronomers set out to answer a straightforward question about the cosmos. If gravity pulls everything together, then the expansion of the universe should gradually slow down over time. For decades, this assumption seemed obvious. Galaxies were moving apart because of the Big Bang, but gravity from all the matter in the universe should act like a brake, steadily reducing that expansion. 2 independent research teams decided to measure this effect directly. The Supernova Cosmology Project, led by physicist Saul Perlmutter, and the HISE Supernova Search Team, led by astronomer Brian Schmidt, began observing distant stellar explosions known as Type 1a supernovae. These events occur when a dense white dwarf star accumulates too much matter and detonates in a thermonuclear explosion. Remarkably, these explosions reach nearly the same brightness every time, making them ideal standard candles for measuring cosmic distances. By comparing how bright a supernova appears with how fast its host galaxy is moving away, astronomers can determine how the expansion of the universe has changed over time. Throughout the late 1990s, the teams collected data from dozens of these explosions across billions of light years. When the results were finally analysed, they revealed something completely unexpected. The distant supernovae appeared dimmer than predicted, which meant they were farther away than expected. And the only explanation that fit the observations was astonishing. The expansion of the universe was not slowing down, it was accelerating. Some unknown influence, later called dark energy, was pushing galaxies apart faster and faster as time passed. Independent measurements confirm the result, with statistical confidence exceeding 7 sigma, a level of certainty that left little doubt the phenomenon was real. The implications were enormous. If cosmic expansion continues accelerating, distant galaxies will eventually disappear beyond the observable horizon. Entire regions of the universe will become permanently isolated from one another. Over trillions of years, the cosmos will grow colder, darker, and more empty. Structures that once filled space with light and activity will slowly fade. But understanding the true consequence of this discovery requires looking far deeper into the future, across timescales so vast that they stretch far beyond the lifetimes of stars or galaxies. To see where the universe may ultimately be heading, scientists began calculating the distant stages of cosmic evolution. In 1974, physicist Stephen Hawking published a discovery that transformed how scientists think about the distant future of the universe. According to Hawking's calculations, even black holes, the most extreme gravitational objects known, are not truly eternal. They slowly lose energy through a subtle quantum process now known as Hawking radiation. Over unimaginably long timescales, black holes themselves evaporate. This realization forced cosmologists to confront a startling question. If even the most stable structures in the universe eventually disappear, what does the ultimate future of the cosmos actually look like? To answer that question, scientists began calculating the long-term timeline of cosmic evolution. For roughly the next 100 trillion years, galaxies will continue forming new stars as clouds of gas collapse under gravity. These stars will illuminate the universe much as they do today, but this era cannot last forever. Gas, the raw fuel required for star formation, will gradually be consumed. Once the remaining gas becomes too thin to collapse, the birth of new stars will come to an end. Galaxies will slowly fade into collections of stellar remnants, white dwarfs, neutron stars, and black holes. Over even longer periods, gravitational encounters will eject many of these remnants into intergalactic space. Galaxies themselves will dissolve into sparse swarms of cold objects drifting through darkness. Then begins an era dominated by black holes. For trillions upon trillions of years, these objects will remain as the last major structures in the universe. But Hawking's theory predicts that they too will slowly radiate away their energy. A black hole containing the mass of our Sun would take about 10 to the power of 67 years to evaporate completely. The largest supermassive black holes could survive for 10 to the power of 100 years before disappearing. Eventually, after timescales almost impossible to imagine, the final black holes would vanish. What remains is a universe filled with extremely dilute particles and faint radiation spread across vast distances. Temperatures approach absolute zero. Energy differences disappear. No large-scale process remains capable of producing structure. This is the state physicists call heat death, the ultimate equilibrium predicted by thermodynamics. The universe does not end in fire or collapse, it simply becomes still. But if equilibrium represents the final state of a finite cosmos, then an unsettling implication emerges. The complex universe we observe today, filled with galaxies, stars, life and consciousness, may represent only a brief phase in cosmic history, and that realization leads directly to a deeper mystery about the nature of existence itself. Because if equilibrium eventually eliminates all gradients and all complexity, why does the universe generate such intricate structure in the first place? That question reveals the paradox at the heart of reality. In 1872, the Austrian physicist Ludwig Boltzmann introduced a powerful idea that reshaped how scientists think about the direction of time. Boltzmann argued that the arrow of time, the sense that the future is different from the past, exists because the universe moves from ordered states to more probable, disordered states. This principle is encoded in the statistical behavior of entropy, but the deeper implication of Boltzmann's work is rarely discussed. If entropy continues increasing forever, then the universe must eventually reach a condition where no further increase is possible. This state is called thermodynamic equilibrium. At first glance, equilibrium sounds harmless. In everyday life, balance is something systems tend to settle into. But in cosmology, equilibrium represents something far more extreme. It is a state where every usable difference in energy has vanished. To understand what that means, consider a vast underground reservoir filled with pressurized water. The pressure allows water to flow through turbines, generating electricity. But once the pressure equalizes everywhere in the system, the turbines stop. The water is still there, but the energy that allowed useful work has disappeared. The same principle applies to the universe. Stars shine because their cores are much hotter than the surrounding vacuum of space. Chemical reactions occur because atoms can move from higher energy states to lower ones. Even biological processes depend on delicate imbalances that allow energy to flow through complex systems. Remove those differences and the processes stop. In thermodynamic equilibrium, matter still exists. Particles still drift through space, but there are no gradients left to power change. Without gradients, no new structures can form, no stars ignite, no planets develop active environments. And without dynamic systems, observers themselves cannot exist. The universe would not end in an explosion or collapse. It would simply become permanently still. This conclusion leads to a troubling realization. If a finite universe inevitably approaches equilibrium, then the complex cosmos we observe today, filled with galaxies, ecosystems, and thinking minds, must be temporary, a brief episode in an otherwise silent history. Yet this conclusion clashes with another observation. The universe is astonishingly good at producing complexity. Galaxies organize into vast structures. Stars assemble planetary systems. Chemistry builds molecules capable of storing information and replicating themselves. Reality appears to generate complexity almost as if it were encouraged. But thermodynamics predicts the opposite trend. So how can both statements be true at the same time? To resolve this contradiction, scientists began exploring a possibility that fundamentally changes how we think about the cosmos. Perhaps the universe does not have a final boundary at all. In 1981, a young physicist named Alan Guth proposed an idea that would permanently reshape modern cosmology. While studying the earliest moments after the Big Bang, Guth suggested that the universe may have experienced an episode of incredibly rapid expansion called cosmic inflation. During this brief fraction of a second, space itself expanded faster than light, stretching the young universe by unimaginable amounts. At first, inflation was introduced to solve several puzzling problems in cosmology. It explained why distant regions of the universe appear remarkably similar, why the geometry of space seems nearly flat, and why tiny fluctuations in the early cosmos eventually grew into galaxies. But as physicists studied the mathematics of inflation more carefully, they uncovered something far more startling. In many models, inflation does not end everywhere at once. Instead, it continues indefinitely in some regions of space. While one region slows down and forms a universe like our own, other regions keep expanding, producing new domains of space-time again and again. This concept became known as eternal inflation. If eternal inflation is correct, then the universe may not be a single expanding system at all. It may be part of a much larger cosmic landscape, where new universes constantly emerge. In this framework, space could be effectively unbounded. Some regions may cool and approach thermodynamic equilibrium, while others are just beginning their cosmic evolution. To understand this idea, imagine an immense field of expanding regions where local environments constantly change. One area may be quiet and cold, while another nearby region is still forming galaxies and stars. The overall system never settles into a single final state, because new regions continue appearing. For cosmology, this possibility carries enormous implications. If reality is unbounded, then equilibrium might never dominate everywhere at once. While some parts of the cosmos drift towards stillness, others may remain active and dynamic. This would fundamentally change how we think about the ultimate fate of existence. The universe might not be moving toward a single universal ending. Instead, it could be part of an ongoing cosmic process, where creation and decay occur simultaneously across different regions of space. And if that is true, then the paradox of thermodynamics becomes even more intriguing. Because an infinite or continually expanding reality would mean that equilibrium is never truly final. It would only ever be local. Which leads to an even deeper question. If the universe never reaches a single terminal state, what does that imply about the persistence of complexity, and the possibility of observers within the cosmos? That question leads directly to the final piece of the puzzle. In 1948, mathematician and physicist Claude Shannon introduced a concept that would quietly influence how scientists think about complexity in the universe. Shannon's work on information theory showed that structure and information cannot exist without differences. Information is created only when systems contain distinguishable states, variations in energy, matter, or configuration that allow one condition to be different from another. In simple terms, information requires contrast. A perfectly uniform system contains almost no information, because every part of it looks the same. But when a system develops variations, clusters, patterns, or gradients, it becomes capable of storing and transmitting information. This insight has profound implications for cosmology. Galaxies, stars, and planets represent enormous concentrations of information. They form when matter gathers into specific structures instead of remaining evenly spread across space. Life itself pushes this process even further, organizing chemistry into systems capable of storing instructions, adapting to environments, and replicating, but according to thermodynamics, such structures should gradually disappear as entropy increases. In a finite universe moving toward equilibrium, information would eventually dissolve. The gradients that support structure would flatten. The processes that allow complexity to grow would shut down. Yet if the universe is unbounded, a different possibility emerges. Even if one region of the cosmos approaches equilibrium, another region might still contain strong gradients of energy and matter. New galaxies could form there. New stars could ignite. Planetary systems might assemble again under the pull of gravity. In that sense, complexity would not need to survive forever in a single location. It would only need a universe large enough that the conditions for complexity continue to appear somewhere. Observers could vanish in one region of space and emerge again in another region separated by vast cosmic distances. From this perspective, consciousness and curiosity may not be rare accidents in a dying universe. They may be recurring outcomes of a cosmos that never fully settles. If reality is truly unbounded, the disappearance of complexity in one place does not represent the end of complexity everywhere. Instead, it becomes part of an ongoing cycle where structure forms, evolves, and fades, only to reappear under the right conditions elsewhere. This possibility reshapes the meaning of cosmic time. The universe would not be moving toward a single final silence. It would be participating in a continuous process where emergence and decay occur across different regions of reality. And that realization leads directly to the ultimate question: if the cosmos never truly reaches a final state, what does that mean for the very idea of an ending? In 2012, data from the Planck Space Observatory, operated by the European Space Agency, delivered the most precise measurements ever made of the universe's large-scale structure. By mapping the faint temperature variations of the cosmic microwave background, Planck allowed cosmologists to calculate the geometry of the universe with extraordinary accuracy. The results revealed something remarkable. Within the limits of measurement, the universe appears to be geometrically flat. In cosmology, flat geometry carries a powerful implication. A perfectly flat universe does not naturally curve back on itself like the surface of a sphere. Instead, it can extend outward indefinitely. Space may continue far beyond the observable horizon, potentially without limit. This observation does not prove the universe is infinite, but it removes one of the strongest constraints that would force the cosmos to close in on itself. Combined with theories such as eternal inflation, many physicists now consider the possibility that reality is vastly larger than the portion we can observe, perhaps even unbounded. And if that is true, the thermodynamic fate of the universe changes dramatically. Entropy would still increase in every local region. Stars would still exhaust their fuel. Black holes would still evaporate over unimaginable spans of time. Individual cosmic neighborhoods would eventually drift toward equilibrium. But equilibrium would never conquer the entire cosmos at once. While one region grows cold and uniform, another distant region could still be forming galaxies. While ancient stars fade in one corner of reality, new stars may ignite somewhere far beyond our horizon. In that sense, the universe would never reach a single final configuration. Completion would remain local. The cosmos would behave less like a machine running down toward a stop, and more like an ever-changing landscape where structure continually appears and disappears. This possibility reveals the deeper meaning of the infinity paradox. A finite universe inevitably approaches stillness. Energy spreads out, gradients vanish, and the processes that create complexity eventually shut down. But an unbounded universe may never allow that final silence to dominate everywhere. Decay would occur. Yet somewhere, conditions for structure could arise again. Galaxies forming, stars igniting, planets evolving environments where chemistry becomes complex enough to organize itself into life. In such a cosmos, existence is not defined by permanence, it is defined by continuation. Civilizations may appear and vanish, entire galaxies may fade into darkness, but the larger cosmic process would remain unfinished. The universe would not be moving toward a final ending. It would be participating in an endless unfolding of structure, transformation, and emergence. And if reality truly has no final boundary, then the future is not a destination waiting to be reached. It is a frontier that may never close.